All right, today we're going to talk about angular momentum and conservation of angular momentum. So here's our chart of comparison of linear motion and rotational motion. And today we're going to talk about the last piece in this chart, rotational motion's equivalent of momentum, which we call angular momentum. So as you'll recall, momentum for things that are moving linearly, we define that to be equal to mass times velocity. So you're not going to be surprised then to see that angular momentum is just moment of inertia times angular velocity. Because we've seen this before, right? We take the equation for linear motion and we replace all of the variables with the angular equivalents, and lo and behold, the equation we get is useful. All right, and so it shouldn't be surprising that if we replace momentum with angular momentum, which we usually represent with the letter L, and if we replace mass with moment of inertia and velocity with angular velocity, we get the definition of angular momentum. Now, if you have a point particle moving at some velocity in some direction, you can find the angular momentum of that particle around some arbitrary axis by simply taking r cross p, where r is the vector from the axis to the point particle, and p is the momentum vector of the particle. Now, if you have a bunch of different particles, you can find the total angular momentum just by summing up r cross p for each individual particle. And as you can imagine, if I had a solid body that was rotating, I could calculate the angular momentum of that body by breaking it up in my mind into infinitesimal little pieces, right? And then integrating, summing over all of those infinitesimal pieces, summing r cross p for each of those pieces, all right? So let's, for example, find the angular momentum for a free particle just zipping along about some arbitrary axis. So imagine I've got some particle of mass m moving with some velocity v in some direction, and I'm just going to choose some arbitrary axis right here and say, what's the angular momentum of this particle about that axis? Well, there's two ways we can think about this. The first way is to do this. We're going to say, look, there is the vector r that goes from my axis to the particle at some particular moment in time. Well, angular momentum is just r cross p, right? And so, well, p is just mass times velocity. And if I take my r vector and extend it with this dotted line right here, the angle between r and p is right there, right? So when I do r cross v, that's the angle that's going to show up in my equation. So the magnitude of L is just the magnitude of this cross product, which is RMV sine of theta. And of course, the direction, using the right-hand rule, the direction of the angular momentum is out of the board, which makes sense because if I put my thumb in the direction of the axis, my fingers show it rotating about that axis in the counterclockwise direction, and that's what the particle is doing. Now, I'm going to label this angle right here as phi, and then I can write my momentum in terms of phi. It's just RMV sine of 180 degrees minus phi, because that's what theta is. But it turns out the sine of 180 degrees minus phi is the same as the sine of phi, so I can write my angular momentum like this. Now, I'm going to just draw a line here of length b, where b is the closest this particle will get to that axis as it flies by. And with that line right there, I have a triangle, and I can show that sine of phi is just b opposite over hypotenuse, b over r. The r's cancel, and I get, that is the the angular momentum of this particle about the arbitrary axis that I picked. The other way I can think about it is this way. Well, momentum, by definition, is I times omega, moment of inertia times angular velocity. So let's find the moment of inertia and angular velocity for this particle. Well, if that distance right there is r, the moment of inertia is just, for a point, mr squared. So there it is. So the magnitude of the momentum is mr squared. And of course, once again, it's going to be, the direction is going to be out of the screen. Now, how do I find omega? Well, first I'm going to label this angle phi as we did before, and then I'm going to draw a line from the end of my velocity vector up to the r vector, which is perpendicular to r. And now I have a triangle. I can write my velocity as a component in the r direction and a component orthogonal to the r direction. So I can think of my velocity in two pieces. There's one piece that's getting it closer to the axis. That's this piece here, and one piece that's making it rotate around the axis, which is the red line there, and I'm going to label that v phi. Well, if I know the velocity at which it's rotating around the axis, that velocity is just r times omega, r times the angular velocity. So the angular velocity is just that component of the velocity divided by r. So there we go, we plug it in. Well, this r cancels with one of these r's, and then I'm just left with v phi, but v phi is just the magnitude of v times, this is the opposite side, so it's times sine of theta. Again, we'll draw this line of length b here, and we can show that sine of phi is just b over r, and we get the same answer. The angular momentum of this particle about this arbitrary axis we picked is mvb. Notice that the angular momentum depends on which axis we choose, all right? Okay, now let's talk about conservation of angular momentum. When we talked about linear momentum, we started with Newton's second law, F equals ma, and then we said, well, look, acceleration is just the time derivative of velocity. And then if I pull mass into that derivative, I have the derivative of mv with respect to time, and m times v is just the momentum. So force is the time derivative of momentum. Therefore, if there's no force acting on a system, the momentum of that system will be conserved. And that's what we saw, right? We have two particles collide, the particles interact with each other, but if the world does not interact with those two particles, if they only interact with each other, then as they go through their collision, we decided momentum must be conserved. Well, you get a similar thing with angular momentum, right? Newton's second law, written in the angular form, is torque equals moment of inertia times angular acceleration. Tau equals I alpha. Well, alpha, the angular acceleration, is just the time derivative of omega, the angular velocity. And now we'll just pull I into that, and then I times omega is just L. So torque is equal to the time derivative of angular momentum. As such, if I have a system and it could be acting, the different pieces of the system can be acting on each other, producing torques, but if there's no external torque acting on this system, that means the change in angular momentum with respect to time will be zero. Therefore, the angular momentum of the system will be conserved. It won't change. Here's an example. We have our particle, right? It's just flying along. Nothing's putting any torque on it. As such, we would expect the angular momentum to be constant. And what we found when we calculated it was indeed a constant. All right? Here's another example. Imagine I have two satellites, one with a mass of 205 kilograms and a moment of inertia of 1845 kilograms meter squared. The other with a mass of 322 kilograms and a moment of inertia of 3,218 kilograms meter squared, and they lock together. Before joining, the first satellite is rotating at 2.62 radians per second, and the second one is not rotating. How fast will the satellites be rotating after they link? Well, we can solve this problem using conservation of momentum. Right? After all, there are no external forces acting, no external torques acting on these two satellites. It's just the two satellites interacting with each other. As such, for the system of the two satellites, the initial momentum should equal the initial angular momentum should equal the final angular momentum. Well, the initial angular momentum, since the second satellite is not rotating, it's just the moment of inertia of the first satellite times the angular velocity of the first satellite. And then the final angular momentum is just going to be, well, both of the satellites are going to have the same final angular velocity, so it's just going to be the sum of their two inertias times omega final. And we can easily solve that for omega final. And then we can plug in numbers and we find, the final angular velocity for the two of them joined together is 0.955 radians per second. We can also change rotation rate by changing the moment of inertia. So imagine I have two masses, and if I conserve momentum but get the masses closer together such that I goes down, if I goes down, omega has to go up. All right, so here's the problem. 2 point masses, each with a mass of 350 grams, are free to slide along a bar of negligible mass which is rotating about its center. A string keeps the masses a distance r from the center of rotation. By pulling on the string, I can change the position of the masses. If they are initially 12 centimeters from the pivot and the bar is rotating at 3 radians per second, how fast will the bar rotate if I pull on the strings to bring the masses a distance of 6 centimeters from the pivot? Well, once again, the string is pulling on the masses, but it's pulling on a line from the axis to the mass, so the strings provide no torque. No torque means momentum, angular momentum should be conserved. So let's do the calculation then. So angular momentum initial must equal angular momentum final. Well, what's angular momentum initial? It's just I initial times omega initial, and that's equal then to I final omega final. And in this case, I is changing because we're changing the distance of the masses from the axis. All right, so I is just for each mass, if we treat them as point masses, it's just mr squared. All right, but there's two of them, so we multiply by 2. So then the initial momentum then is just 2 mr initial squared times omega initial, and the final angular momentum is just 2 mr final squared times omega final. All right, the 2's and the m's cancel out, and we can easily solve this then to find the final angular velocity, and it's just equal to the initial radius over the final radius squared times the initial angular velocity. And then we plug in our numbers, and we say, oh, because it goes as a ratio of the radii squared, because we're cutting the distance, the radius, in half, the angular velocity is going to go up by a factor of 4, and we end up with 12 radians per second. Now, notice that if omega changes and I changes, in this problem they changed in a way such that the angular momentum was conserved, but the kinetic energy was not. Then we can show that, right? Because we know how the rotation rate changes as we change the radius. And with that, we can find how much the kinetic energy changed. So the rotational kinetic energy is just 1/2 I omega squared. So the change in kinetic energy is just 1/2 I final omega final squared minus 1/2 I initial omega initial squared. Well, we have our formula for omega final, and of course I is just 2 times mr squared. So we plug this in for our final I, this in for our initial I, and we plug this in for our final angular velocity, and that simplifies down to r initial squared omega initial squared times r initial over r final squared minus 1. So because r final in this case is smaller than r initial, the kinetic energy went up. Where did the energy come from? Well, we're pulling on strings to pull the masses closer together, right? And if we're making the radius smaller, that means that we're pulling the mass inward as the mass moves inward, so that's positive work. So we can also calculate changing kinetic energy just by calculating the work we do to pull the masses in. Well, the work done on the two masses is just twice the work done on one mass, and the work done on one mass is just the integral of the force, the tension in the string, times distance from the initial to the final distance. Well, of course, tension is the force on the string, which is keeping the ball going, keeping the mass going in circular motion. And so we know that the force is just the mass times the acceleration, and we know that the acceleration, because it's going in circular motion, is just v squared over r. All right? And of course, v, the velocity, the tangential velocity, is just omega times r. So we take omega times r squared and use that to replace v squared. And then, here's the equation we had. We just remember that omega is r initial over r squared times omega initial, right? We found that using conservation of angular momentum, that the final omega is just the r initial over r final squared times the initial omega. All right, and then we have an r squared here, cancels one of those r's, and so we get an r right there. All right, so this is right here, that's just omega. Now, we can pull everything out of this integral that does not depend on r, everything that's just a constant. So we have our 2, we pull out the mass, we can pull out omega initial, we can pull out r initial, and what we're left with in the integral then is just 1 over r cubed dr. And that's easy enough to integrate, right? That's just the integral of 1 over r cubed is 1/2 1 over r squared, all right? Well, technically negative 1/2. I dropped my negative. That's okay because I want to find the work. Okay, yeah. I dropped a minus sign, but I also needed to put another minus sign in order to get the right sign for the change in kinetic energy. So I'll just leave it at that. But anyway, this can be simplified to what we had gotten before. All right? Okay, the final thing we're going to talk about is gyroscope. So a gyroscope is just basically some device that has a moment of inertia and you can spin it really fast so that it has lots of angular momentum. So we're going to spin this silver ring here on our gyroscope, and so it has lots of angular momentum. Now gyroscopes are really cool because with that angular momentum, there is a resistance to changing the direction, right? If I do things to this system that don't produce torque, I can produce all the forces I want. If I don't produce torque, I won't change the angular momentum, which means I won't change the direction of the angular momentum, and my gyroscope will continue to point in the same direction. So you see right down here, we've got our pivot moving around in different directions, but the gyroscope still pointing in the same direction. So this can be really useful. For example, they're used in airplanes, so you can always tell which way is up. So your airplane moves around, but this gyroscope, it's always pointing up, and so you can tell which way up is. But you have to be very careful to mount your gyroscope in such a way that you don't produce torque, because if you do, torque is equal to the rate of change of angular momentum, right? So if there's torque, there's no guarantee that your angular momentum is going to keep pointing in the same direction. In fact, a common thing you see with gyroscopes is something called precession. And precession happens because there is a torque acting on your gyroscope. For example, imagine I have a gyroscope here, but its direction of its angular momentum is not straight up and down. It's tilted off to the side by amount. So gravity's pulling down, but there's a torque due to gravity because our pivot point is down here. Here is the lever arm, and here's the force due to gravity. So now they are, if the gyro was straight up and down, the angle between r and the force of gravity would be 180 degrees, and you get no torque. You do the cross product and you get 0. But if it's tilted by some amount beta, then we're going to get a torque on our gyroscope. All right? Now, torque is the time derivative of angular momentum. So if you look at this, r cross mg, if you do the right-hand rule, you find the torque is pointing into the screen. All right? So if I just take my gyroscope and it's not rotating, I put it on the pivot and I let go, the torque is going to make it fall over, right? If I put my thumb into the screen, my fingers are curling in a direction that say, it's going to fall over, just like we would expect. But what if the gyroscope were spinning and it already had a really big angular momentum? Well, if we rotate the whole system downward, kind of in the intuitive direction, that changes the angular momentum in this direction. But that's not the direction of the torque. The torque is into the screen, right? So that's not what happens. Instead, the gyro will rotate, right? So I start right here. I add a little angular momentum, right? Because torque is the rate of change of angular momentum. So if I have a torque in a little bit of time delta t, the angular momentum will change a little bit delta L, which is in the direction into the screen, and boom, so it rotates. So with time, that rotation just continues, and we get what is known as precession. So our gyroscope is spinning, and it has a high angular momentum, and the torque due to gravity, instead of making it fall over, it makes the gyroscope precess in a circle. So we can calculate how fast it precesses. All right, so here's the angular momentum of our gyroscope at time t equals 0. And we know that the angular momentum is going to rotate around this pivot and trace out this circle. Okay, and here's the angle beta. That's the angle between the lever arm and gravity. Now, torque is the time rate of change of angular momentum. It's dl over dt. Well, let's solve this for dl. If I just multiply both sides by dt, I find that the angular little change, infinitesimal change in angular momentum is equal to torque times little change in time. So in that little change in time, how big and in what direction is dl? Well, dl, right, is going to be into the screen. So it's this little vector right there, right? Now, this distance right here, if this is L, our angular momentum, this distance right here is L sine of beta. And then after we add our little infinitesimal dl, what we've done is we've rotated our angular momentum vector a little bit, and we get this line right here. And if we call the angle between those two d theta, well then the little change in angular momentum, dl, is just L sine beta. That distance, it's just this arc of the circle. It's just a little piece of arc on the circle. So it's just the radius of the circle, which is L sine beta times d phi. All right? Now, the rate at which it will precess, the angular velocity for the precession, is just the time rate of change of phi, right? But from this equation right here, we can see that d phi is proportional to the torque, and we can solve this for d phi over dt, and we get then just torque over L sine of beta. So that is the rate at which the gyro will precess. So the gyro is spinning with some angular velocity omega, but then because there's torque on the gyro, the direction of that angular momentum will change with an angular velocity omega p for precession. All right? So once again, going back to our gyroscope video, so the angular momentum of our gyroscope at any given time is along that bar right there. The disk is spinning really fast, but that angle is going to rotate. All right? It's going to change. So omega p describes how fast the bar is rotating, and omega describes how fast the disk is rotating. All right, and let's come back here. So, of course, L, the angular momentum of our gyroscope, is just I times omega. And what is the torque due to gravity? It's just going to be this distance r times mg times sine of beta, right? So the magnitude of the rate of precession is r mg sine of beta, and that's all over I omega sine of beta. The sine of betas cancel out, and there we go. There is the rate of precession of a gyroscope due to gravity. Now, if we're clever, we mount our gyroscope in such a way that the lever arm is 0, and so gravity doesn't produce torque. And people work really hard to make what they call gimbal mounts for gyroscopes that don't introduce very much torque. Okay, let's work a problem with this now. A top consists of a disc with a mass of 200 grams and a radius of 2 centimeters, with a thin pointed rod going through its center, as shown in the figure on the right. The point of the rod is 2.5 centimeters from the center of mass of the disc. So if the center of the mass of the disc is in the middle of the disc, this distance down here to the point is 2.5 centimeters. If the top is spinning with an angular velocity of 200 radians per second, with its rotation axis tilted 25 degrees from vertical, how long will it take the top to precess one complete circle? All right, so we want to find how long it takes for this angle to rotate around and come back. And incidentally, the moment of inertia for a disk spinning about its axis of symmetry is just 1/2 mr squared, and we'll use that. So remember, the period for something going in a circle is just 2 pi over the angular velocity. So that means we need to know the angular velocity. Well, we don't want the angular velocity of the top, we want the angular velocity of its precession. All right, and we found that earlier. We found in the previous slides, we found that that is rmg over I omega, but we need to be careful, right, because there's two different r's in this problem. There is the distance from the center of mass to the point, and then there's the radius of the disk. And the equation we found here, this r is the lever arm of gravity. All right, so that would be the distance from the center of mass to the point. So I'm going to very carefully call that r pivot. All right, so if we plug that in for omega, we'll get the period of precession. But first we need to know what I is. Well, I is 1/2 mr squared, so we can plug that in. The period of precession is just 2 pi omega precession. And omega precession is just r pivot mg over I omega. Oh, dang, I left off my pivot there. This is r pivot, right? And then when we plug in, here it is. I fixed it there. Good. Then when we plug in I is just 1/2 mr squared. So the 1/2 cancels this, and then we're going to get an mr squared. And this is the radius of the disk. This is the pivot. That should also be our pivot there. Don't let that confuse you. All right. Well, the masses cancel out, and there's our answer. We plug in some numbers, and we find it takes 1.02 seconds for the top to precess around once. So the top is spinning 200 radians per second. It's spinning many times many rotations per second, but once per second, the angle of its rotating axis will precess once. That's the end of our video for today.